So Man and I are here to present Transportation Surge Analysis Prediction Program. So this is a project we've worked on within CDOT for the last couple of years. And I gotta say, I've been in this industry for over 20 years, and this is probably one of the coolest projects that I've been a part of. So hopefully after this presentation, you'll be able to appreciate that. Thanks. There we go. All right, so a quick outline here. I'm going to give a background, kind of genesis of the program. We're going to talk about the goals of the program and application, talk a little bit about the data behind it and how we process it, and then we're going to get into the AGL application, do a little, not a live demo, but show the functionality of the site, and then talk through some use cases and next steps. I'm going to start on the next slide. So I think everyone in this room is aware that North Carolina is susceptible to hurricanes. There's been over 400 known cyclones that affected the state. And these metrics aren't even updated for this year, which we've already had a couple active events. 16 have made landfall over the last 27 years. And the high watermark for those, pun intended, was Hurricane Florence in 2018. I do want to take a minute to talk about Feynman, because Feynman and then associated with that Feynman T was kind of led us into T-SAPP. But probably a lot of you know about Feynman. It's a statewide gauge-based flood warning system that's active both on the coast and in rivers inland. It provides near real-time awareness of flood impacts and potential damages to buildings around the gauge location. And Feynman was really successful during Hurricane Florence. It was used a lot, provided a lot of awareness. Unfortunately, when you have an event like that, where you have major roadways, including I-40, I-95 going underwater, there were a lot of questions that were being asked specifically of DOT that Feynman couldn't answer at that time, associated with what roads are passable, how long are they going to be flooded, how can we get to certain locations. So Feynman T was then developed, and that application could do a whole nother presentation on that, but that provides awareness on road inundation impacts and also bridges. But both Feynman and Feynman T are still somewhat limited in their capacity on flood warning, and you are only able to see what's around the gauge location. So in between gauges, there's a gap there. They do both have planning tools, scenario tools, that allows you to do what if the water level is a certain amount, what would you see, what would happen. And also there's limited forecast ability on both sites based on where River Forecast Center provides information. So in comes T-SAPP, advanced slide. So T-SAPP is an application that we developed that was intended to help fill those gaps and also give advanced awareness along the entire coast of the state. So it's a system that uses ad-cert modeling from the UNC Rincy Center and is able to produce seamless mapping along the coast and also provide that advanced awareness based on hurricane advisories that are posted. Here we go. So here's an example of just Tropical Storm Idalia and an advisory that was posted for that event, and then the associated T-SAPP application on the right there that shows the storm track, and then Amanda's going to go in detail on the associated information that's available. Next up is goals for T-SAPP. So again, the primary goals for the system were to provide advanced awareness of potential impacts from tropical events along the coast, to provide seamless coverage of the entire coast, and also to create inundation mapping and inundated road products that were available at the street level view scale. Also, we wanted to build in the ability to compare previous events to current events and also other past events. And also really important was the ability to report out to senior leadership. So we needed to be able to provide really succinct metrics about potential impacts that could be passed along to other decision makers. And before I hand it off to Amanda, also want to give recognition to the UNC Renzi Center, Dr. Rick Ludick and Brian Blanton at the UNC Renzi is a Renaissance computing center, and they're the ones that are getting the hurricane advisories and running the abstract models and publishing those results onto a server that we can then access and kick off our process. Here we go. Amanda.
All right. So here we have the overall workflow of what T-SAPP is going to be doing during an active storm event. So let's say we have, a tropical storm, cyclone, or hurricane currently going on. The National Hurricane Center team start issuing their advisories. Those advisories, we have 4 of them. They come out at intervals every 6 hours. RINC, the research group that Matt just mentioned, they kick off their abstract model runs every time the National Hurricane Center posts an advisory. Those model runs, they vary for how long they take the process. We usually can access their results in about 2.5 hours from when they start kicking off. And then we are able to download their model results from the server. Okay. And so once those model results are posted, then we have a script to download a script that will kick off and get the model results from RINC. And then we will use that to start processing our data. So once we kick off our geoprocessing effort, we're going to end up waiting around 1.5, it can go up to 2.5 hours, depending on the number of predicted impacts. And so while that geoprocessing is occurring, then we're usually babysitting the application, making sure that no errors are being logged from our Python script, and keeping everything, keeping the lights on, so everything's running. Once everything's finished developing, then we go ahead and publish it to our T-SAPP application, and our downloader script will then go back in its checking mode, where it's going to start looking at the RINC server about every hour to see if we have an updated advisory uploaded. So the RINC data actually has pretty extensive coverage. It runs from the Gulf of Mexico all the way up into our northeastern states, and that data. Sorry, very good. So obviously we have a lot of coverage for that data. Everything you're seeing right now is a product of the RINC forecast. We do not do any forecasting in the T-SAPP application. This is just the model straight from their abstract data. And so what we're looking at here are locations where their model has predicted maximum water surface elevation, and that's what we're going to be using for our processing. They do have a time series that they've included for when the maximum water surface elevation will occur at one of these locations. We currently aren't implementing that in T-SAPP, but we do plan to do that. And so obviously, since this is a very large coverage of data, we are only interested in looking at the impacts to coastal North Carolina. So we have a boundary that we're going to use to narrow down how many points are going to be used for processing. We still end up with over 58,000 points, so it's still pretty dense coverage. And our boundary for the extent that we use was created using previous storm surge, there we go, cool. So this boundary is the outline in red that we use to clip our data to the North Carolina coast. And this boundary was developed using historical storm surge from large hurricane impacts from the past, as well as our floodplain data. So like a second, I always know what's going to come next. So more about this data that we're using from RINC. Obviously, we can view it as points in the slide, but we're accessing the data as a .net/PDF file, which is a multi-spectrum data format where you can see time series and other environmental factors. But we're just looking at the maximum water surface elevation. So when we access our data from RINC, we're getting it as that .net/PDF file, and then we're going to convert it into a table with the lat long and then max water surface elevation, so that we can use it for our geoprocessing at points instead of the .net/PDF format. We use the inverse distance weighting method to interpolate our water surface elevation and create a raster. And so now we have a water surface elevation raster once we get to that part of our processing. reason why we're using a raster water surface elevation is because we have to derive our flood depths, and what we use to get to that point is terrain for our coasts. And so we have our So we have our water surface elevation raster created, and then we also have a raster of our terrain, and we are just subtracting that terrain from our water surface elevation to come up with these rasterized flood depths. And so this flood raster is going to be used further in our geoprocessing, but we also want to be able to see the extent of inundation in the T-SAPP application. So we're going to run through some steps to simplify, smooth, and delete any small pockets of flooding to create a more simplified polygon view of our inundation. And that's going to be used in T-SAPP as a polygon. That will look really cool in 3, 2, 1. No, okay. Anyways, that's my polygon. This one gets published to T-SAPP, and then we use it in our application so that we can display the flood extent. But obviously, we're not just showing flood extent. We're also going to show our mapped roadway impacts. And so in order to get to our roadway impacts, we have to start with our input data, which is going to be a master data set of all of our roadways in our coastal divisions, which are 1, 2, and 3. That data we downloaded from NCDOT to start with as just their GIS polyline data, and they've attributed it with everything meaningful that we want to use, so like route name and route class. And then it is really great data to start with, but it's not quite perfect. We have to do some corrections in order to get it to align with our LiDAR data for our roadways. And we also just want to make sure that the actual alignment of the roadway is correct, that it's mapping to every cross street. This data we like to develop by the route name so that we can then split it into 50-foot segments that we're going to use in our analysis. And that's just a level of detail that we chose to get pretty decent results out of it. So we've only had to do this, at the beginning of our modeling. We don't clean up the data, brand new data set every single time, but we do go back into this initial input data and clean it up whenever we have any kind of errors from our model or something looks kind of wonky. So we have to start thinking to advance before I hit them. But so we do need to assign flood depths to our roadways, and that's going to be part of our geoprocessing model. We are extracting the maximum inundation value from our segment. It's going to overlay the flood depth raster, and then that maximum depth value is going to be used to assign a depth category. And for us, a depth category just is a range of flood inundation. So let's say we had a max depth of like 2.8 feet, then that roadway segment is going to be assigned a depth category of 2 to 5 feet of roadway inundation. Then once we have our depth categories assigned, we like to involve everything by the depth category as long as it's a continuous segment of the same road name. And we'll use that for our symbology moving forward into the T-SAPP published data. On the application, we publish our data to the our GIS server. And then every time we're publishing a new feature or new advisory data to this endpoint, we are also going to be copying the previous advisory data into an archive feature class. And so every time our automation process runs, we're going to be overwriting previous advisory data, and then T-SAPP will be updated with the latest and greatest. Our T-SAPP data is available to view on 2 applications, or 2 interfaces, I should say. One is a legacy, what we're calling a legacy web application, and that's a very map-centric view. NCDOT and ESP decided there was a need to see more of a integrated interface, where we're looking at a map view, but then we can also see tables and apply filters and quickly move through the data as if we needed to send out a report as quickly as possible. So we decided to move to the ArcGIS Online platform, and that's where we have our dashboard plugged into an experience builder. I'll get into why we chose to embed a dashboard experience builder screenshot of T-SAPP. Now the suspense is good. This is a big reveal. So this is the look of T-SAPP as it stands right now, or pretty closely to as it stands right now. you can see that we have multiple widgets configured in here. We have our map view, of course, and that's where you're going to see the map roadway impacts, and those are symbolized. You can use this table right here to kind of get an idea of what the symbology is, but they're symbolized by that depth category they were assigned. We also have our division boundaries and counties in that map view as well. And then this table right here, this table at the top left of the screen, we're calling it a coastal impact summary, but it is the summarized miles impacted by depth category, sorted class. And we're using interstate, highways, NC routes, secondary routes, and non-system routes for this analysis. We also have, something to plug in about this table, the way that we have those, rows color is by using Arcade. So that's just kind of another reason why we like to move into the ArcGIS Online arena, is that we can use Arcade here, and a lot of GIS analysts are pretty comfortable in that language versus JavaScript or something. And then underneath this, also this table is selectable. So if we wanted to filter out our impacts by depth category, we could select a row here and it'll filter out our map accordingly. Then we have a list below that initial table, and that list contains multiple descriptive fields about each roadway that's affected or predicted to be impacted. And that list is searchable. We'll have a slide kind of going into more of that. So within our map interface, if we wanted to kind of get more of a detailed look at one of the roadway segments, I think we've gone down to a pretty decent zoom level. This isn't quite as detailed as we can get. There'll be a slide that gets even further, but at least in this view, you can see community impacts. So we're looking at community of Woodrow, and we can see there's a decent amount of roadways that could be impacted, one of which is crossing a stream, which is something that's important to note. We have a pop-up that will show the road name as well as the next step, and then the ability to open up a Google Maps Street View. So this is an even more detailed look at a predicted impacted road. We got here by using the list widget to type in a street name, and then that list was filtered, and our map extent got zoomed to where we're just looking at the Orchard Creek Road impact, and we're able to also, of course, change the base map. If you want to make a customized base map in here, then you can do so as well. And then another helpful tool for reporting is, of course, being able to summarize impacts by geographic divisions. And so in this table, we're looking at the number of miles impacted by county. You can see them as the depth category or as the route class. And so this just gives us an idea for a more overview, looking at any obvious standout number of impacts. We're just looking at the county in this, we're just looking at county impacts for this graph, but we also have implemented a graph that shows impacts by division. So if we really just wanted to, even further overview, we can do that. One of the benefits also of using a dashboard is the ability to use selectors. So here we're using a selector to filter out all divisions except Division 1. And then we can see, obviously, for Hyde County, there is a high number of impacts. And that helps us for our reporting so that we can then look into Hyde County, which roads are affected, and give that report to NCDOT or any local emergency management. And so one other dashboard we've created, this is very similar to our prediction T-SAPP dashboard, but this is actually hindcasts. Hindcasts are the observed water surface elevation impacts that are modeled by RINC. So after a major hurricane, they're going to run their model on the observed maximum water surface elevation, and then we run that data for T-SAPP, and we kind of get an idea of which routes were likely to have been affected from a major storm. So here, I think we have 6 storms. I think that's still accurate. We're showing 6 hindcasts currently in T-SAPP, and we can use our drop down to see those impacts. We can also see the storm track, and that's helpful because let's say that you were expecting a storm of similar impact to hit a specific area where you remember a previous storm, maybe Fran, had a large impact. You can look at what happened during Fran, which roadways were affected, and compare that to maybe your current T-SAPP advisory or another HITAP. In this case, we're looking at the city of Wilmington for Fran versus Matthew. And there's a pretty obvious change in inundation. And I think we all know that those are different storms. I was very young for Fran, but I heard about it. The T-SAPP plan next. So for T-SAPP plan next step, we have plenty of room to grow. And so when it comes to functionality reporting enhancements, we're always looking for feedback from our stakeholders, into DOT community to incorporate more ways to summarize our data. We've included evacuation routes as well as the DOT assets and what we're reviewing now. We also are looking into including predictions for bridge monitoring locations. We're still hanging in there for hurricane season 2023. We've been active for 2 storms so far running T-SAPP, and again, learning lessons along the way, but also it's given us plenty to implement for hurricane season 2024. So even though there will be hurricanes in between those, we will stay busy with T-SAPP updated. There's also talk of, if we were in Raleigh at our office, if we were impacted by a major storm, we would want to keep the lights on for T-SAPP. So we're looking at possibly migrating to a cloud environment or utilizing servers in one of our other office locations during storm events. So that's where we're looking to move forward next. And it. So if we have any questions, we can do that, or we can talk about ways that we've been validating our data.
Hold on 1 second. Okay. One of your bullet points was the next steps was monitor bridge location. Is that replicating Bridge Watch functionality, or are you looking to replace Bridge Watch?
They're definitely not looking to replace Bridge Watch. We would be utilizing, so Bridge Watch currently incorporates AdCert predictions for their hurricane advisories. And so similarly, we would want to do the same thing, but we would just want to be able to show the impact from T-SAPP as well. So the same data source, just another way to view it. That's really all it would be. Bridge Watch also takes on a lot of hefty analysis when they're showing their data. They've got Slosh and AdCert as well as the real-time gauge impact. So it could also be kind of a backup.
Hi, I believe that you mentioned that you downloaded the roadway data at the beginning of this process. Do you anticipate updating this data as new projects are completed?
Yeah, absolutely. So luckily, since this is a project in collaboration with NCDOT, they've been pretty good about keeping us updated whenever they have any major roadway construction. I think Jughead is a good example of a bridge that was updated. For Jug Handle, not Jughead. Jughead is the more confusing. Jug Handle. Bridge is an example of one that we did update. So the one case where burning bridges is a good thing is when you're updating them in your raster.
Is there any parallel with this and FinMT, or like do you guys work off of any of that data? Or is it kind of the same? Does it? Because I know FinMT is kind of more inland. I'm not sure if this is just for the coastal area or how that works.
Yeah, obviously this application is focused on the coast, but there are coastal sites in FinMT. Like I kind of presented at the start, FinMT is based on actual readings at gauge location, whereas this is a whole different product based on the data source from the coastal surge model. And FinMT is limited in the extent around those gauge locations, whereas this provides a seamless view of the whole coast. We do have some really interesting kind of validation slides where we have compared, for example, what FinMT was showing and what T-SAPP had also predicted. So probably won't have time to show that, but happy to come by the booth and I can walk some more.
Maybe we have time for one more question. Anyone else?
Yeah, so is this application just internal use with the DOT, or are they sharing with any of their external government partners?
It is limited and not public facing right now. It's specific for DOT. They have shared it. We've had, like the U.S. Coast Guard has had interest in it. So there have been some other stakeholders that have reached out and have been given access to it.